I say we need courage for this. Why courage? Because again, science is a way of life, which I always remind my students. Your journey will take a very long time, but nonetheless, it will be very beautiful and very rewarding. By the way, in connection to having this type of engagements, I wish also to invite all of you for the 22nd PBM National Physics Conference this October 17, 24, and 31. Earlier, we have the first session. And if you want to know more, you can visit the SPBM webpage. Another thing, when I came back, I find it very difficult to do research in the institute in MSUIIT. There are many reasons for this. For one, I don't have a laboratory, okay, a laboratory space. Second, I have no equipment whatsoever. And the most important is that I don't also have students to work with. Thankfully, my training allowed me to develop, and with the help of my, at the time, limited number of students, make these devices. Little by little, we have developed our laboratory from nothing to a laboratory capable of doing cutting-edge experiments in optical manipulation, for instance, in soft matter and biological systems. This journey took a very long time to happen, and I really appreciate the help that I get from everyone, especially from agencies that gives us financial support. Another big problem that we faced at that time was the fact that we are in Mindanao. Um, Being in Mindanao means that due to the security situation in some areas, not so much equipment suppliers can provide you with what you need. And oftentimes, the laboratory materials that we need comes very late. But nonetheless, we persevere. And I hope this is my second point. Let the difficulties that surrounds you as a scientist or as a physicist inspire you to be better, not the opposite. Let it inspire you to do more and inspire you to go higher. Okay? So those are the two messages. Science is a way of life. And second, persevere. We are not in a first world country. We will face a lot of hurdles. But as scientists and physicists, we need to go beyond these things and compete as well at the stage of our international peers. I think our speaker today, Dr. Bernardo and his group at NIP with Ian, also went to the same hardships, but conquered it all to make a gravitation research foothold in the country. My prayers that we all enjoyed the talk this afternoon and that all of us will be inspired. I thank once again the organizers for the kind invitation and most especially for organizing this already a series of meetups. Uh, I know that a lot of the young people that is joining this activity will be inspired to do and take a life of a physicist. So once again, thank you everyone, and let's enjoy the afternoon. God bless us all.
Okay, for the introduction of our guest speaker, we will now have Mr. John Dello.
Hello. Yeah. Good afternoon, everyone. Thank you for attending this physics meetup. Yeah, it's my pleasure and a great honor to introduce to you our very special guest from the National Institute of Physics, University of the Philippines Diliman. So our guest speaker is a very simple man, very friendly, and easy to talk to. He just recently completed his PhD studies at the National Institute of Physics and awarded as the most outstanding PhD graduate student. His work is mainly on the scalar tensor theories of gravity, in which he combines the scalar fields with space-time to create a theory for us to understand how the universe have formed way, way back in the past and how it evolved into its present state. He attended schools and workshops abroad. Just last year, he attended the workshop on general General Relativity and Gravitation and the 2019 Asian Pacific Winter School and workshop on gravitation and cosmology in Japan. He also attended the summer school on cosmology in 2018 at Abdus Salam International Center for Theoretical Physics in Italy. His research interests are the following: cosmology, dark energy, scalar tensor theories, black holes, gravitational waves, analog gravity, and semi-classical gravity. For the record, he already published 13 scientific papers in journals with high impact factors. And as a trivia, I have a trivia for you guys. Did you know that our speaker loves watching anime? Yes, he does. As just his background, it's from Naruto. And also, he plays chess. He's good. He's very good at it. Yeah. Now, without further ado, I know everyone is very excited. Me, even I myself can't wait. Let us welcome with a virtual round of applause to the Philippines' first homegrown gravitational physicist, Dr. Reginald Christian Reggie Bernardo. A round of applause.
Thank you. Thanks, John Dello, for the introduction. Last night, I was actually able to break my 1800 barrier, 1800 barrier tawag doon, rating in chess.com. So that is a small milestone for me, but I mean, you got to celebrate those milestones. So nag-chess ako kagabi actually hanggang kanina bago itong meetup, and yeah, I was able to break that barrier, and tagal ko na try i-break yun. Thanks for the introduction. So let me share my slides now. Where is it? Yeah. So thanks again. So let me just start off with this exciting news. Room temperature superconductivity has been achieved, and very likely narinig yun actually yung news. This was just 2 days ago, but well, just in case you haven't yet checked it out, here's a copy of the Nature paper, nandiyan yung citation. Of course, that's really easy to find right now. Type nyo lang actually room temperature superconductivity in Google, and definitely you're going to end up with this paper. So check that out. That's very nice, and that's very big news right now. I wanted to show this. Kasi yung kung naalala nyo yung teaser actually for this physics meetup, you have there basically an object in the teaser is actually an H-shaped trajectory. That's one of the possible trajectories of an object in a black hole binary system. So what's shown in this slide right here is a depiction of a binary black hole solution, and the analytical solution to that is actually known to be the Majumdar-Papapetrou solution. So you have two black holes right here, you have a black hole right here, you have a black hole right here. And yung H-shaped trajectory na yun is a geodesic, and a geodesic is an actual trajectory in real space. So ito yung ellipse, or ito yung elliptical orbit ng planets, ito yung could be hyperbolic orbits and so on. So yung H-shaped trajectory na yan, that's an actual, that could be an actual trajectory of a photon or any object moving really fast around a black hole binary. Again, the solution is called the Majumdar-Papapetrou solution. So natuwa ako nung pinakita sa akin ni Adele yung teaser, because it's one of the few solutions that actually exists in GR, in general relativity. So that's a very nice fact right there. Okay, so well, if you want to check this out, check this paper. So this was published last year, the physics of black hole binaries. by Laura Bernard, Vitor Cardoso, Ikeda and Zilhao. So just check it out. It's really nice. Letter yung paper na yan. So actually nakatago yung details, but of course pwede nyo naman i-check yung references nila and then i-check nyo yung details for yourselves. So yeah, let me now start my talk. So teaser lang yun. So I wanted to talk about a brief history of black holes and cosmology in the Philippines. I am not actually going to talk about myself in this talk, but if you have any questions like that or questions specifically pertaining to how this all happened and specifically how this all happened with me, you're welcome to share in the comments. First, ang madaming misinterpretation sa title na naibigay sa akin by the local news. Yung pinaka-dangerous interpretation is matatanggal nila yung homegrown. So by then, some would misinterpret I'm the first Pinoy gravitational physicist, but as I'm going to show for the rest of this talk, I'm not, and I'm far from being the first gravitational physicist Pinoy. And it's let's just check it out. So instead, I have used this very special title right here. Ako yung gumawa. So wala namang naghumingi ng opinion ko nung actually nagbigay sila ng title sa akin. So here is my own title for myself. I am the first stubborn PhD graduate in PH in the Philippines specializing in gravitational physics, because the typical, if you want to do gravitation and cosmology, usually what you would do is to apply abroad and then get your degrees abroad. And we've had already Professor Ian and Professor Reina in the physics meetup. Both of them have obtained their PhDs abroad. So in my case, nandito si Ian. He is my PhD supervisor. PhD supervisor, and I stayed with him with this group for 3 years, and then I was able to obtain my PhD degree. And yeah, so let's just talk about that. So thank you again for the invitation. I'm Reggie Bernardo. So here's the topic of my talk. I'm going to talk about black holes in cosmology. I'll start by talking a bit about black holes in cosmology, end up with the 2020 Nobel Prize in Physics. Basically, I just want to point, I'm going to point that this is one of the few things that we can learn by looking up at the stars and observing the galaxies, well, among other things. And then for most of my talk, I would talk about the work done, the contribution of Filipino scientists to this 100 years old field of black holes and cosmology. So yung black holes have been predicted as early as Einstein equation has been produced. It's one of the earliest solutions of the theory. So it's fair to say that the field is actually as old as general relativity itself. So it's more than 100 years old, and I'd like to address what have we contributed to this very exciting scientific field so far, and then what can we expect from the future. Yeah, so what can we learn by looking up at the stars? So I'll just leave that question a bit for 10 seconds to think about that, and so madami tayong sagot. I'm going to have likely different answers. A different answer, so just think about that for a bit. Kung gusto niyo pala ako interrupt, informal naman yung session, you think some really nice question, just go ahead and put it out in the comments. So nakabukas yung chat sa akin. If pag may nakita akong magandang tanong, I'll answer that immediately. Yeah, so let me go back to this. What can we learn looking up? Say you observe the sun, you observe the planets and so on. You like to look at the stars. Yeah, so what can we learn from doing that? So my answer would actually be a lot of things. There's chemistry, biology, biochemistry. I think last 3 weeks ago we have there was this big news of a sort of gas that, as far as we know, can be produced only by biological beings in Venus. So may mga speculations of life, possible life in Venus. But that's one of the things that we could actually speculate by observing the stars. But here I am going to talk about the physics that we can learn by looking up at the stars. And out there's one fundamental interaction that dominates everything else. And I'm sure you know what that is. And then yung dahilan kung ba't tayo nag-enjoy manood ng basketball, NBA, PBA, and so on. So the answer is gravity. And yeah, so this is what gravity looks like right now. So if you haven't been in touch with gravity, yung last equation na nakita nyo is Newtonian gravity. Basically, force is proportional to the mass, inversely proportional to the square of the distance between the two massive objects. So that's captured by this equation now. So ito lang yung equation na ipapakita ko sa slides na to. This equation is known as the Einstein equation, and that basically this equation is basically where the entire subject of gravitation and cosmology revolves around right now. So basically yung mga part ng mga ginawa ko sa thesis is about basically solving this equation for black hole solutions, for cosmology, discussing cosmology na pwede natin makuha dyan, and so on. So Newtonian gravity is completely captured by that. Yung elliptical orbits, it's completely captured by that. But this is the general theory of relativity. This is the superior generalization of Newtonian gravity. Basically, it tells that gravity doesn't actually attach to the mass. Ayun yung sinasabi ng Newtonian gravity. Gravity attaches to the energy. And because of that, we're going to have a lot more exciting predictions. We're going to have light bending. So light is made up of particles with no mass. So what you'd expect is, in the end, if you're just doing Newtonian gravity, in the end maapektuhan ng gravity. But then Einstein gravity, general relativity would say instead that gravity attaches to energy. So light has energy, so gravity can bend light. So yung pictures dito basically show yung earlier predictions ng GR. So dadalian ko lang tong slides na to. So you have here, ito yung nagpanginig kay Einstein way back. So he was, of course, first making up his equations way back in before 1915, and then he wanted to calculate he calculated very precisely and accurately the precession of perihelion of Mercury, and that's something that Newtonian gravitation alone cannot accommodate. So of course, the orbit of the planets around the solar system is approximately elliptical. But then kapag in-observe mo actually yung orbits, yung elliptical orbits na yun is nag-move kagaya niyan. So in that way. And pinakamalaking observed precession for Mercury, for the reason na ito yung pinakamalapit yung orbit sa Sun. So dyan, ito yung magandang test case. And check out the story. Madami kayo makikitang pop science articles about this. Ito yung nagpanginig kay Einstein nung na-calculate niya correctly ang amount ng precession ng Mercury. Then we've had immediately other solutions to the Einstein equation. Ito yung nag-convert basically to ito yung nagpa-superstar status sa level ng general relativity way back, the observation of light bending by the sun. So this was a famous expedition. Just check out the articles about this. This was a famous expedition in 1919 by Arthur Eddington, confirming the light bending as predicted by general relativity. And as I said, light has energy, so it should be able to be affected by gravity as well. So light would not be moving in this straight path. For instance, say may star ka dyan sa may location na yan. So to reach us at Earth, of course, light should travel from the star to Earth, but then say the sun is between the star and us right here. So magbe-bend yung path. Instead, we're going to observe the apparent location of the star right here. So check out the very nice articles about that. And then they did a lot more solutions. They've discovered a lot more solutions of the Einstein equation. During the 1920s, we've had Friedman's. So Friedman is a cosmologist. Friedman's solutions to the Einstein's equation, basically predicting that the size of the universe or the universe itself would actually be dynamic. Ibig sabihin, nag-evolve yung size niyan, could grow bigger or larger. It doesn't have to be static. Which was the leading theory back then. Okay, so then yung madaming observations during the 1920s by astronomer, specifically astronomer Vestus Slipher, ng redshifts ng galaxies. Basically, you have light coming from galaxies. Turns out, kapag nag-observe ka ng light na ganun, and then you compare them to what we expect from the lab, redshifted yung light, ibig sabihin mas mababa yung energy nila, and a possible implication of that is actually galaxies are moving further away from us. And then that's something that could be grounded in the general relativity as well. And from that, we're going to get to the idea of the expanding universe, eventually to the leading Big Bang model or lambda CDM model today. Okay, madaming tanong sa chat, so pipili na lang ako ng isa. What's the difference between special and general relativity? So special relativity was published in 1905. General relativity was published in 1915. And the biggest difference is basically special relativity, tinanggal yung gravity doon. So Einstein has basically wanted to check out what a theory without gravity is. And then he needed 10 more years to figure out what could be the actual theory of gravity. So yan yung the difference. Sana nasagot ko yung tanong from Jacob L. Can photons experience time? Yeah, the answer is yes. So may measure din sila ng time. Questions about singularity, I think I'll just try to answer again later kasi maggagawa ko ng malaking time jump to 2020 from now. So yeah, let's do this. So many things have happened since way back. I mean, it's the field is 100 years old. You have black hole solutions, you have stars, you have a lot of theorems about things. But of course, this is what captured our attention 2 weeks ago. So the Nobel Prize in Physics 2020, yeah, of course, 2020 is a memorable year because of the pandemic. But now it's going to be memorable also because this is the year the Nobel Prize in Physics was awarded to black hole theory and astronomy. So the award was given to Roger Penrose, Reinhard Genzel, and Andrea Ghez. So Penrose was working with the theory of black holes. Reinhard Genzel and Andrea Ghez was working on the astronomy side of black holes. Basically for the discovery of Sagittarius A star, the supermassive compact object at the center of our Milky Way galaxy. And kung may technical questions kayo about how that was discovered, I could try to answer that later as well. Okay, so I'm going to talk more about the work of Roger Penrose. So basically, Penrose, the award was given for this work for the discovery of that black hole formation is a robust prediction of GR. But now I'm going to answer actually what that means. Okay, so by first telling you about a bit about black holes. So check out this picture on the right hand side. Buksan ko lang yung chat. Wala ko yung chat. Yung the very first solution to black hole solution way back was by Schwarzschild. So it's a black hole mainly because there's a place, kapag na-cross mo na yung place na yun, there would be no turning back. Because if you want to turn back your trajectory, you're going to have to move faster than light. So that's how it works. But this is one of the problems with one of the things that people pointed out about black holes way back. Now, the solutions would possess typically two singularities, and singularities mean places kung saan kapag in-evaluate mo yung equations mo, you're going to get an answer of 1 over 0. And of course, you know what 1 over 0 is. That's infinity, and that's not allowed to well, as far as we are concerned, that should not occur in nature at all. So that's so kailangan mo i-question yung calculations mo. So may possible kaya na real entity itong black hole because it has singularities. So there are two singularities. So the first singularity is actually yung place na kapag na-cross mo, hindi ka na makakapag-turn back. And that's the so-called event horizon. But the thing about the event horizon is it's not an actual, it's not a real singularity itself. It's actually just it's actually just there because you've used some funny coordinate system in general relativity. So there's funny way of using coordinate system in general relativity. Kapag ito yung nagamit mo, you might end up with what you might immediately think of as a singularity. But then may isa pang singularity. So event horizon is actually not there, so hindi man yung singularity, so there's no problem right there. But there is a singularity at the location r is equal to 0 of the black hole. So that's something that should be addressed. And then yung tanong ng typical question about that is kasi nung nakuha natin yung black hole solution, we've assumed a lot of symmetries, spherical symmetries, spherical symmetry among others. So yung speculation doon is perhaps we have obtained the singularity because we've assumed spherical symmetry among other things. So and then this is where Roger Penrose's work comes in. So his answer was no. So Roger Penrose, what Roger Penrose did back then was basically to remove all of those assumptions. At the same time, he invented and basically converted the field of general relativity into a more mature superior formulation. He invented the notion of trapping surfaces among other things. Basically, as shown, even if you remove all of those symmetries, spherical symmetries, you're still going to end up with a singularity. And this thing is actually now known as singularity theorem. So basically, you have a surface of a collapsing star, and then you move forward in time. Palaging liliit ng liliit yung surface na yun. Eventually, the surface would coincide with the Schwarzschild radius of the collapsing object, and then it would become a black hole. And then following that trajectory into the future, still the singularity would actually still be there. That's what it means to be black hole formation is a robust prediction of general relativity. Okay, so I think pag isipin nyo lang yun for 5 seconds, namatay yung aircon ko, buksan ko lang ulit saglit. Yeah. Yeah, sorry about that. biglang uminit dito. So check kung may mabilis na tanong. Sorry, hindi ko pwede sagutin lahat ng tanong. Wala tayong time, but I'll probably just pick one at random. So from Eliza Lodronio, isn't there a point where a black hole cannot be collapsed any further? Well, as far as we know, once yung surface nga, or the trapping surface would coincide with the event horizon, as observers outside of the looking at the black hole outside at the event horizon, wala na tayong makikita sa loob actually. So the surface, the trapping surface would further continue to contract as far as theory is concerned, and then there should be a singularity still at the center of the black hole. But we're not, as far as astronomy goes, we're not going to see that kasi ang last place na makikita natin sa black hole is the event horizon of the black hole. But yeah, well, as far as theory goes, the singularity would still be at the future of the black hole, and there's just a future. It's going to be right there. So by black hole cannot be collapsed any further, I'm not sure if what you mean by that is the event horizon, but well, yeah, the event horizon is would be a sufficiently stable place where pwede mo i-consider na yung black hole na hindi na siya nagko-collapse. So once the event horizon forms. Okay, thanks. So now let me just check out this next work. So in practice, you can't actually talk about the work of Roger Penrose without talking about his work with Stephen Hawking. So Roger Penrose has shown that the singularity lies at the future of the black hole. Hindi ko pala nabanggit sa last slide. So once you are inside the event horizon, the R is equal to 0 would actually lie at the future of the black hole. So hindi yan center, that's actually R is a time coordinate inside, so the singularity is at the future of the black hole. His work with Stephen Hawking basically has traced back this singularity to the past as well. So basically assuming, so palaging itong mga theorems na itong may assumptions, for this work by Roger Penrose and Stephen Hawking, the assumption is that you're starting from general relativity. So doing this and then playing the motion picture basically backwards. So may motion picture ka na ng universe na nag-expand. Now play that backwards. And what Stephen Hawking and Penrose basically has shown in the 1970s is that there's going to be a singularity as well in the past. And of course, that's what we refer to as the Big Bang model today, as the Big Bang. Sagutin ko lang na mabilis. There's a question: Hawking radiation could be considered the death of a black hole too. So when you try to combine now quantum mechanics and general relativity, well, not a superior combination, but basically assuming that quantum mechanics sufficiently holds, WKB approximation ng tawag, if you are interested in doing this technically, you're going to end up with Hawking radiation. So basically Hawking radiation basically means that particles could be produced outside the slightly outside the event horizon of the black hole, and by doing that, kailangan mabawasan yung mass ng black hole unti-unti. So kapag yung mass ng black hole is proportional to the size of the event horizon. So kapag nababawasan yung mass, eventually mag-shrink yung black hole. But then eventually actually mag-heat up yung black hole while contracting. So that's actually counterintuitive to how we perceive heat capacity and other things. Kasi habang lumiliit yung mass niya, mas umiinit yung black hole. So that's Hawking radiation, and yeah, you could maybe consider that the death of a black hole. But the thing about Hawking radiation is that sobrang faint niya. So yun lang gusto kong i-note about Hawking radiation. It's very, very faint. Ibig sabihin mahina lang yung. So you're going to take you're going to need years to be able to well, hilahin mo lahat ng energy ng black hole and then make it collapse to whatever final state there is. So for instance, you're going to need 14 billion years to remove 10 to the 15, ano ba yun? 10 to the 15 grams from a black hole. So you're going to need 14 billion years to do that. So basically primordial black holes that would have died today. Okay, so madaming tanong, sana masagot ko pa mamaya. Okay, let me just play around a bit. So may dalawang impostors dyan sa picture. So who are the impostors in this picture? Yeah, okay. So you have here Benedict Cumberbatch. That's Stephen Hawking. That's Benedict Cumberbatch. And then that's Eddie Redmayne from Theory of Everything. So kung gusto niyo panoorin yung movies. Okay, so I can talk. I can spend definitely more time talking about the big guns in gravitational physics, but as promised, I wanted to instead focus this talk basically on the contribution of Filipinos to this approximately 100 years old scientific field. Basically, contribution of Filipinos to black hole physics and cosmology. Okay, so this basically answers that I'm not the first Pinoy gravitational physicist. The first Pinoy gravitational physicist is Professor Roger Posadas. And by the way, to avoid talking about impostors in the field, so wala yung just to narrow down this search and yung criterion for picking out the guys that I would introduce in this talk, I'm going to narrow down my search to Google Scholar and other existing scientific repositories. So dapat makikita natin yung papers nila online. Yun. So this is the first Filipino gravitational physicist, Professor Roger Posadas. And then this is his work with Professor Ezra Newman back in 1971. So kapag i-take note niyo yung year, of course, take note niyo yung year na yun sa Pilipinas, but then take note that that was almost the same year that Hawking and Penrose published their singularity theorem, their singularity theorems. So the title of this work is Motion and Structure of Singularities in General Relativity, and this was published in the Journal of Mathematical Physics. So if you need the link to that, ito yung DOI. So I don't want to read the abstract, but it's basically about the Lorentz Dirac equations of motion, which is what you'd get by analyzing basically the motion of a point charge in an electromagnetic field and in a gravitational field. Yeah, so that's the work of Professor Roger Posadas. Professor Roger Posadas has obtained his PhD in, as far as my research has shown, 1970 from the University of Pittsburgh. Then ito yung work niya, his supervisor was Ezra Newman. Newman is a big guy in relativity and specifically in black holes. Kapag nag-work kayo sa black holes, you're going to definitely end up seeing the Newman-Penrose formalism for rotating black holes. You're going to end up seeing the per-Newman electrically charged black hole. So Newman is a really big guy, and you have there Professor Roger Posadas. Professor Roger Posadas would then go back to the Philippines after this. He would become the first dean of the College of Science in UP Diliman. He would also become a chancellor of UP Diliman. But this I wanted to mention that this specialization would not actually be sustained. But for reasons that I can't speculate without much further information kung bakit di niya masusustain yung specialization na yan way back. Okay. So here is another landmark paper as well. So by Filipinos in work related to black holes. So you have here the paper Summation over Histories for a Particle in a Spherical Orbit around the black hole. So this is a landmark as well kasi yung and I wanted to show this kasi yung affiliation ni Professor Posadas earlier was University of Pittsburgh. Now this is the first, as far as I know, first international publication by Filipinos that is affiliated on black holes that is affiliated with the Filipino institution as well. And what else could it be? It's the Research Center for Theoretical Physics in Magna Bohol. And who else could have done this? But we have Professor Christopher Bernardo in his advisee back then, Glenn Aguarte. So this is their work. Not actually an expert on what they did here, but yeah, it should involve a lot of integration. They're closing out an integral, the Feynman path integral for black holes. Yeah, and that's a very important historical paper as well. Professor Bernardo has obtained his PhD in 1982 from the State University of Albany in New York. And then this is his work in 1997. Okay, so this one is very important as well. Kasi after this, you're going to notice that a sort of lineage would now form, an academic lineage would now form, because he's going to be the mentor of the next two persons that I would be showing in this talk. But wala na, hindi ko actually kailangan introduce yung dalawang next na yun because they've been to the physics meetup and they're bigger, they're really big guns. I'm sure we know about them. But let me just talk about this. This is Professor Gerald Garcia's thesis in the University of Syracuse. So Professor Gerald Garcia's thesis is time symmetric initial data in general relativity. So that's actually very important in if you're going to do numerical relativity in the future. That's going to be an important work. Professor Gerald Garcia has obtained his PhD in 1988 from the University of Syracuse. And yeah, this is his thesis, so please try to check it out. Professor Garcia would work at the Ateneo University and retire at the Ateneo University, and he would be the mentor of the next two big guns that I'm going to be showing. So the next one would be kilala ni John Tello. So of course kilala niyo din. He's been in the physics meetup way back. I think June or July. So it's Professor Ian Vega. So Professor Ian Vega has obtained his PhD in 2008 from the University of Florida in the US. So and he's the first person that we could actually talk has sustained his work on black hole physics the first Filipino has sustained his work in black hole physics. So yung mga earlier na pinakita ko sila Professor Posadas, Professor Gerald Garcia, Professor Bernardo, limited lang yung work nila on black holes. Ian would publish really a lot of articles, papers on black holes. If you're interested about this, please do check it out. His work in Google Scholar, just type Ian Vega, and I'm sure you're going to stumble upon his many very interesting work. And ito lang yung nilagay ko as highlight kasi ito yung mga papers niya for the PhD. So this is Ian's first paper published for his PhD. It's with his PhD supervisor back then, Professor Stephen Detweiler. The title is Regularization of Fields for Self-Force Problems in curved space-time. And then this is another paper by Professor Vega, Self-Force with 3+1 codes, a primer for numerical relativists. And this is a very important work, The Motion of Point Particles in Curved Space-Time, published in 2011 with Professor Poson and Professor Adam Pound. So please do check it out. And may physics meetup naman with Ian. So if you're interested, you could check it out. I think available naman yung videos online. So please do check it out. Yeah, okay. Professor Ian Vega would go back to the Philippines in 2015 actually, but then his appointment with the University of the Philippines National Institute of Physics would start in 2016, and he would begin the gravity group, which I'm sure we could say is the first sustained gravitation and cosmology research center in the Philippines. And then dun din ako manggagaling. Yeah, there's also no need to introduce the next person in this slide. We have Professor Reina Reyes. Yes, so this is her published. Hindi ko sure bakit may red marks dito. Hindi ko alam saan galing yun. So this is Professor Reina Reyes publication way back in 2010. Of course, we've all heard about that confirmation of general relativity on large scales from weak lensing and galaxy velocities. And by that, it actually means that if you want to confirm general relativity, you have to compare it with some other theories. And as far as I know, I think nandito si Professor Reina. So this work was compared with the FR theories of gravity. Thanks. So that's, of course, I can't really talk about that in detail right now, but please do check it out. That's available in, available in Nature, and Professor Reina's right here if you want to talk to her. I'm sure you can chat her right now. And yeah, so this is Professor Reina's work. Paki-correct Professor Reina kung magkamali ako sa info. Professor Reina has obtained her PhD from Princeton Astrophysics in 2011. Yeah, so so pa-correct na lang kung nagkamali yung date ko, 2011 or 2010. Thanks. So let me now move on to this. So I'm showing here the work by John Tristram Acuña and Professor Jose Perico Esguerra. So dynamics of a planar thin shell at the Taub FRW junction. So the paper is in the International Journal of Modern Physics. So please do check it out as well. So this is the a work done in general relativity by researchers in UP Diliman. Of course, now Professor Jose Perico Esguerra is while a professor at the National Institute of Physics. John Tristram Acuña is a PhD student at CISA in Italy. So abangan natin actually, I think he's graduating next year. So let's so abangan natin kung ano yung graduation niya. Yeah, and then this is their work as well. So I just wanted to put that out. Dyan sa mga pictures na yan, katabi actually nila ako. Professor Esguerra was my undergraduate and MS supervisor. So katabi niya ako dyan sa picture na yan. So that was taken during my undergraduate graduation in 2015. Ito namang picture with Tram, katabi niya ako. Nasa Venice yan sa Italy. Nung bumisita ako at sa ICTP. Yeah, so I just wanted to show that as well. Okay, so I think matatapos na itong talk. Yeah, so let me finish this in 5 minutes actually. So the gravity group, Ian would then go back to the Philippines. 2016 would be the establishment of the gravity group, and finally we have what appears to be a sustainable gravity research center in the Philippines. And many of the members of this group are, of course, my friends, Jendet Ogaling. And these are the guys, the members of the gravity group. So just for fun, I think madami sa atin kilala si John Dello, and so Ian has been speaker as well. So try to spot Ian and John Dello in the pictures if you have 10 seconds. Yeah, okay, so John Dello's right here. Nasaan siya dito? Ayan, John Dello's right there. Present sa inuman. Ulitin. Di ko sure kung nasaan siya dito. I think na-crop yata, na-crop yung picture na yan. But well, yeah. Of course, you can spot Ian as well. So check nyo lang si Ian. So that's the gravity group. Ito yung gravity room. You see there may magnetic whiteboard. Actually, may pangalan gravity at NIP at the National Institute of Physics. And then ito naglalaro lang actually kami. And then this one is another formal picture. So half formal, half just while playing around. So that okay yung mga yan. So this is the website of the group. So check it out. Well, actually search na lang si Ian. I'm sure you're going to stumble upon the group's website. And then yeah. So now after talking about the bunch of works by Filipino scientists in black holes and cosmology, so yung observation you actually dapat doon, observed yung years. We had a publication in 1970, the 1980s, and then 2008, ang lalaki ng time jump. So we never had yet before a sustainable gravity research center in the Philippines. Ang lalaki ng time jump. And then hindi siya masusustain. So bakit kaya? And then 2016 came, bumalik na si Ian sa Pilipinas, nasa NIP siya. So then he would author a bunch of work by Filipinos and Filipino-affiliated work on black holes and cosmology. So you have here from yung malalaking time jumps na yun, then came 2016, you have 2016, 2017, 2018. So check nyo yung years. So this is the Google Scholar of Ian. And then 2019, 2019, and 2020 works. So pag chinek nyo, this is his first paper with a Filipino MS student. Then Jezreel Castillo is now in the US. So ito yung publication nila ng MS din. 2019, so this is the work with Carlo De Leon with gravitational lens deflection by two power law densities using the Gauss-Bonnet theorem. That's with Ian Vega. Carlo is summa cum laude in UP, Diliman. And then these are my PhD publications. So check nyo yung 2019. So 2 works on black holes, 1 work in cosmology, and then may pahabol ako on black holes na I think lalabas na din. So hintayin nyo na lang. So I am sure that the group would continue to work on black holes in cosmology. If you're interested in this, may Facebook page sila, may website yung Gravity Group. If you want to connect, just send a friendly message. I'm sure they'd be very interested to talk to you about that. Okay, so I'm going to end this with 5 minutes, and then sana masagot ko lahat ng kami nakakilala kay Elizabeth. Sana masagot ko lahat ng technical questions. But basically by asking what lies ahead, ano yung inaabang natin in terms of gravitation and cosmology research in the Philippines. So check out Professor Reyna's group now at the National Institute of Physics as well. So she's heading the NAP Data and Computation Group, and together with Ian in the Gravity Group, they're establishing the first gravitational wave astronomy community in the Philippines. So if you're interested in gravitational wave astronomy, interest naman nag-start lahat, but you don't know anything about the technical details, but you want to learn about the technical details, please do connect with them. Yeah, so check that out as well. Okay, so dito na mag-end yung talk. So say you are interested in gravitation and cosmology, what can you do? Of course, you can study physics in undergraduate, and then afterwards, the most reasonable thing to do is to actually go and study abroad. So apply for scholarship abroad, and then so Ian, Professor Reyna has done that. Yeah, so that's a reasonable thing to do, and you can do that. But now there's an alternatives. Ian's heading the Gravity Group. Professor Reyna is heading the Data and Computation Group. So you could actually connect with them if you want to study gravitation and cosmology in the Philippines. And then say you're as stubborn as me, you don't want to go abroad. So that's going to be an option as well. Yeah, so you could go to the National Institute of Physics. So that's where the specialization, this research specialization seems to be centered at right now. If you're a graduate student, you're going to need money to be able to do this. Hindi mo pwedeng ginagawa mo lang to for interest and wala kang bayad. So you could apply for a DOST scholarship. For MS students, the stipends, the salary is about 25,000 per month, 25,000 pesos per month. So check out the scholarships available from DOST. And then for PhD students, it's 33,000 pesos per month. So John Delo is a PhD student right now. So paki-correct na lang ako kung tama yung amount, John Delo. Yeah, and then after that may scholarship ka na, you can basically do whatever you want. So you can sit all day thinking about black holes, solving the Einstein equation, doing astrophysics and cosmology. You're interested in dark energy, may mga nakita akong tanong sa chat. You can now do it with these stipends. Alternatively, in my case, nag-work ako as an instructor at the National Institute of Physics. So yeah, so well, with that, nakuha ko din yung PhD ko. So during MS and PhD, nag-work ako as an instructor. So I'm studying black holes in cosmology while teaching at NIP, electromagnetism, and among other things. So that's what you can do if you're interested in gravitation and cosmology. And then more on what you can do if you want to stay in the Philippines. I'm going to leave with some questions, basically some key issues about this specialization right now. So far we have Professor Ian, Professor Reyna, but there are only 2 of them. And how many students do they have right now? I think I'm going to estimate around 50 students. So that's going to be very, very challenging. Actually, struggling ng lahat ng scientists natin sa Pilipinas. I'm sure ang daming students, mag-isa ka lang, may pamilya ka, you want a life as well, of course. You have to have a life outside of research. Well, if you want to stay sane. Yeah. So that's a problem. Eventually, I'm sure I'm going to help out with this effort as well. After I sort things out on my end. But I'm going to leave that as a key issue. So in daming students, you have two experts so far. Funding for postdocs, equipment, funding postdocs, I think would actually help out with this first key issue kasi mga postdocs have their specializations. Pwede sila makatulong sa advice ng students, paggawa ng research sa lab, and among other things. Another big key issue is equipment and procurement specifically. So I'm sure procurement would trigger a lot of scientists in the Philippines. That's a word that many, well, as far as I know, many hate. So procurement of scientific equipment is a really nasty business in the Philippines. So that's another key issue. Grant applications. So basically, just put it there to point out ano yung kinds ba ng research na gusto nating bigyan ng funding sa Pilipinas. Do we just want to fund those with immediate impact? I don't know, like beautification type research or something na may makakatulong for mental health and so on. Dun ba natin i-limit yung funds natin? Or do we want to fund actually real science, which is patient and would actually wait for a while to get a result, but would be a real scientific result? Yeah, so I just wanted to put that question out as well. And then availability of jobs. We'll say you become a cosmologist like Professor Reina, you become a black hole, strong gravity theorist like Ian, then you want to go back to the country. You type, I don't know, cosmologist or physicist in LinkedIn or JobStreet, and well, tell me what you're going to find. Yeah, so that's another issue that I put out here as well. Of course, you could apply for professorship, but not everyone. I mean, not everyone who wants to do research wants to teach as well. Say for example, I'm sure na nanonood, madami naman nakapanood ng Big Bang Theory. Sheldon Cooper isn't teaching, gumagawa lang siya ng research full time. So imagine, and I'm sure we've had a lot of Sheldon Coopers already in the Philippines, kaso hindi sila mag-grow sa ganitong klaseng environment. So if you want to do your job as a theorist, say for example, you will be forced to teach 9 units or 12 units, 15 units of teaching workload per week. So this one of the challenges that I see as well. May konting full-time research positions, but as far as I'm concerned right now, konti lang siya. And yeah, so I'm going to end my talk with that. It's already 3 o'clock. So yeah, I think that's it for me. Thank you for listening and sorry for going over time. Yeah, thanks.
So thank you for that, Dr. Bernardo. Good afternoon, everyone. I'm Ken. I'm from the University of Science and Technology of Southern Philippines, and I will be your moderator for this afternoon's Q&A session. So there were already questions earlier that were answered by Dr. Bernardo, and we're going to continue it now. So again, we're so privileged to have here with us Dr. Bernardo. We thank our speaker for sharing with us his research and experience with us, and also for sharing with us the brief history of cosmology here in the Philippines. Thank you again, Dr. Bernardo, and we are excited to learn more from you through the interactions that we will have with
Thanks.
with the participants. Yeah. So to everyone in Zoom, So to everyone in Zoom, may I encourage you to ask your questions directly to our speaker. By this, you may click the raise raise your hand icon, and only when we acknowledge you, we will unmute your microphone. So we have one already here waiting. So, but before that, please state your name first and then your affiliation. But if your signal isn't stable, you may write your questions in the chat box and I will read them for you. We are also going to read some questions from our Facebook Live participants. So we have here some hands already raised, and I'd like to acknowledge Lynn Andre John Bitin to ask his questions. So, Mr. Lin or Lin, are you there? So, Lin, so I think Lin is not yet with us. So, may may I acknowledge another person? We have here Dean Mark Katiil. So, Dean Mark,
Sir,
you
good
may.
afternoon, sir. Good afternoon, everyone, and to all the participants in this conference. I would like to ask Mr. Bernardo. Um, the thing is, I would like to ask that from the quantum electrodynamics, from there, it stated that um, electricity and magnetism are being united through a force called messenger particles or related to particle physics. So I'm asking is if it is possible in the field of gravity to fully understand it if there's a messenger particles behind the force of gravity like the quantum electrodynamics.
Dr. Bernardo. I think Dr. Bernard lost his signal. Let's just wait for him for a while. And we are joined here with, in Zoom, we have 376 participants, and we also have some participants in Facebook Live. So let's wait muna for a while, Dr. Bernardo. So if you have, again, if you have questions that you want to ask Dr. Bernardo directly, you may use the raise your hand icon in Zoom. So wait lang daw muna, sabi niya. So Dr. Bernardo, are you back? Are you back with us?
Yeah, I'm right here. Thanks. Sorry,
Uh,
hindi ko sure bakit nag-lag yung internet.
so is Dean Mark still here? Can you
Yes,
repeat the
sir.
question? So can you repeat the
Sir,
question to Dr. Bernardo?
sir. Good afternoon, Mr. Sir Bernardo. In quantum electrodynamics, it is stated that the force between electricity and magnetism are carried by virtual particles. So it is united to form a quantum electrodynamics. So is there a possibility that in gravity there a messenger particles which uh, which behaves or which will explain the force of gravity, which because gravity is can affect object and with vast distances.
Hello?
Sir,
Do you hear it, Dr. Bernardo?
Yeah, na-pick up ko actually yung ibang words though hindi naging clear. Okay lang. I want to request actually type and ask the question while doing so. So kapag lag, narinig ko na lang din.
Okay. So request daw po niya na pa-type na lang din po daw yung questions.
Yeah,
I think his
thanks.
question is about
So I think the question's
messenger
about
particle.
basically the graviton. Tama ba ako?
Yeah,
So,
the messenger particle for gravity.
yeah. I don't know the answer. I don't know. So as far as electromagnetic fields are concerned, and have already confirmed the theory of quantum electrodynamics. Yes, indeed we have photons, but in contrast with that, kasi the reason why we can check that out is because of the coupling of basically the photons with the electromagnetic field and quantified yan by constant, the fine structure constant, which is approximately 1/137. So that's very small, but it's something that we can check out at the labs. For gravitons, however, yung coupling constant na yun would actually go as far as 10 to the minus 11 last time I checked. So if we want to check out basically the existence of gravitons in the lab, we have to be really precise. And by mentioning 10 to the minus 11, ang binanggit ko actually is basically coupling of the coupling of gravitons with other objects during inflation. So inflation is what we speculate to happen way back 14 billion years ago. But if you want to measure the coupling of gravitons right now, I think it's fair to say that it's almost impossible. It would be the coupling constant would be 10 to the minus 120 as far as I remember. So 10 to the minus 20. I mean, how are you going to measure something as precise as that? Yeah. So if the question is about basically detecting the graviton, there's a chance that we can do that. And the chance to do that, I think, is basically look for gravitons. I don't know, free streaming or during inflation. So that coupling is 10 to the minus 11 during the inflationary era, and then that would couple with the matter fields, with the matter back then, the inflaton. Then of course there'd be reheating. The inflaton would be converted to fermions and bosons. Other things would create the chemical elements. Yeah, and then yung coupling strength is 10 to the minus 11. So there's a chance to see that by looking at the cosmic microwave background. Thanks. So sana nasagot ko yung tanong.
Thank you, sir.
Okay, so we have
Yeah,
here
thanks.
other hands that were already raised. May we or I'd like to acknowledge first Miss or Christine Salatan Cabato to ask the question directly to Dr. Bernardo. So Christine. Christine, can you hear us? So since Christine is not yet here, let's acknowledge another person. Let's call Von Philip. So Von Philip, you can ask the question.
Eh sir, ang tanong ko po ganito. Okay, ito po. How the black holes how the black holes may tanong ko how the black holes located and how it
Hello?
formed. Hello, sir. Ulitin ko po, how the black holes located and how it formed. Ibig ko sabihin, sir, saan po ba nakikita yung black holes? At paano po ba siya nabubuo? Sa yung black holes na
Yeah, thanks. Yeah, so how do black holes form?
Opo.
Well, you begin with a star. That Lovon. You begin with a star, and well, if you want to go way back, you begin with a gas that would then eventually collapse under its own gravity. So then you're going to have a star. And then a star is characterized by an internal pressure, that gravitational pressure that tends to compress the star. So liliit siya ng liliit. Plus nuclear fuel, which would instead push the components of the star outward. So naglalaban yun. And as long as the star has nuclear fuel, so as long as may nuclear fuel siya, then you're going to have a stable star. But then eventually the fuel would run out. Nuclear fuel, hydrogen, helium, nuclear process, and so on. Eventually the fuel would run out. And then, so wala nang magbabalance dun sa gravitational pressure mo. So after that, the pressure of gravity would continue to contract the star, compress the star. Eventually, so I'm going to mention Hooke conjecture ang tawag dito in relativity. Hooke conjecture is basically you put an object inside a ring na yung size niya is so-called Schwarzschild radius, then that's when you're going to have a black hole. So eventually magko-contract yung star kasi wala na siyang fuel. And then, well, it could actually end up as a white dwarf or a neutron star if madami siyang electrons or neutrons, or may sufficient electron and neutron degeneracy siya. But let me skip that part. So eventually magko-contract siya, and if yung size niya would now be smaller than the size ng surface, basically size ng star, is smaller than the Schwarzschild radius. If you want to compute this, the Schwarzschild radius is 2 capital G, Newton gravitational constant, the mass of the star, over c squared. So that's the Schwarzschild radius. Kapag mas maliit na yung size ng star compared to the Schwarzschild radius, then that's when you become a black hole. That's when the star becomes a black hole. And then the Schwarzschild radius of the star would mark the position called the event horizon. So ayun na yung last place actually na last place in time kung saan natin actually makikita yung events na nangyari sa star. So we're not actually going to see the star collapse. Yung final moments ng star as far as we are observing from infinity would maglalag siya mula sa atin. Hindi natin makikita yung final moments ng people in the star that would then collapse to a black hole. Yes, sana nasagot ko yung tanong mo. So if we're talking about solutions of theories, they are a solution when black holes are solutions when you remove all the matter components in your equation. So tanggalin mo lahat ng matter. Dun sa pinakita ko na Einstein equation, basically remove yung right-hand side, and then you can get a black hole solution. As far as astrophysics is concerned, ganun nga, you begin with a star, and then nawala na lahat ng nuclear fuel, it would compress and compress. Eventually, it should become a black hole. If it doesn't become a white dwarf or a neutron star.
Okay.
Yeah, thanks.
So let's call another person. We have let's call Luisa Reza. Luisa Hereza to ask the question. Luisa?
Hello po. Hi, Dr. Bernardo. My name is Luisa Raza and I am currently taking up STEM strand. So my question is, do we have information or various theories that a wormhole can possibly do exist? And if yes, what are those?
I think we lost him again. Let's wait for him.
Hello. So sorry, naglalag yung internet ko. Not sure. Actually, ngayon lang ako nakasama sa Zoom meeting na may, I don't know, 400 participants. So nag-struggle yung internet ko actually.
So, can we repeat the
I
question,
think okay
Luisa?
na.
Okay na yan.
Yeah, thanks pa ulit.
Luisa? I think Luisa was asking about the possibility of wormholes. Is it really true or not?
Oh yeah,
Or
yeah,
can
yeah.
it really exist?
That's actually very interesting for me kasi kahit ako nag-investigate ako ng wormhole solutions, we don't know yet. So wormholes are solutions of the Einstein equation. As long as you provide some weird exotic matter in it, so you put this exotic matter, exotic in the sense na may mga i-violate ng certain energy conditions. Well, it may not if you put some more assumptions in it. But then, as far as we know, we haven't yet detected wormholes, and the hope to detect wormholes right now is actually through by using gravitational waves. Because now that we can finally measure detect gravitational waves, unique ang signal ng black holes, unique ang signal ng wormholes. So kapag nakita mo yung wave na nakuha ng LIGO or Virgo, it's specific for black holes, black hole binaries. It could be specific for wormholes as well. Yeah, so that's how one way we can actually detect wormholes. Well, we haven't yet detected it yet, but if Einstein equation is correct, they should be there. They should be there as well, as much as black holes are there. Though may yung plot twist sa wormholes is the addition of exotic matter. So ayun yung plot twist sa wormholes. So if you're thinking interstellar, you got to have some kind of exotic matter, some five-dimensional being or something like that. Thanks for the question.
May I just ask another question related to that? How about white holes?
Yeah, sure.
What's your opinion about those?
Not sure as well. Not sure about white holes as well. Well, actually, hindi madaming experience ko doing white holes, so I can't actually answer anything concrete about white holes. Sorry about that.
Sure. So let's just read some questions in the chat box. We have here from Gian. hello, Dr. Bernardo. I'm Gian, currently an applied physics student. So are there any plans to expand Gravity Research Group in Diliman to other universities? And do you have existing collaborations with Philippine SUCs? Thank you for hearing us out.
Thanks. Well, as far as I'm concerned, alam naman ni Ian to, alam din ng girlfriend ko. As far as I am concerned, I would like, alam nga din ni Biento and ni John Delo, I would like to actually work outside of NIP in the future. So kasi I think if we want to make this kind of research sustainable, we got to expand outside of the National Institute of Physics. Doon na may mga existing challenges nga din doon. You have dalawa lang sila so far, so because of that na-attempt din ako bumalik sa NIP. But then as far as I know right now, free agent ako ngayon. I'm not affiliated with any institution right now. I could go anywhere I want. Though very likely magtatrabaho muna ako sa ng postdoc in a few years, but then I'm a free agent. So if we're talking about NBA, I'm a free agent. I could go to well, wherever I want. Do what I want. So pwede ako sana makapunta din ako sa CMU someday. Actually. Nakikita ko yung pictures ni John Delo sa Instagram. And of course, si Bien, sinasabihan din ako dati, CMU looks really, really good. Sana mapuntahan ko din ang CMU. But as far as plans, I'm sure may plans din si Professor Reyna, Professor Ian. I'm sure we can talk to them about that as well. Sila naman yung mas madaming experience din. And sila yung may established groups na on gravitation and cosmology. So as far as that is concerned, NBA champions na sila. Ako free agent lang ako muna ngayon. So hanap ako ng ring.
Okay. So we have so much questions in the chat box, but I'm afraid that we can only accommodate one last question. If the universe stopped expanding and started shrinking by the Big Crunch theory, will the universe shrink twice the speed of how the universe expands? Also, after the universe has shrunk, will the universe once again expand and create the same celestial body, or will it create a new celestial body?
Yeah, hanap ng tanong ah. So it should depend on the matter content of the universe. So the thing about our universe so far is, well, as far as the current model of the universe is concerned, and that's the lambda CDM model, may component kasi ng universe na nagpo-push ng components niya outwards, and that's dark energy. And the thing about dark energy is constant kasi yung energy density niya. So ito short crash course on cosmology. Paki-correct ako, Professor Reyna. Yung basic contents ng universe, ingredients ng universe is basically you have baryons, you have radiation, and then you have dark energy. Madami pang things, but they're basically negligible. And then what happens kapag nag-expand yung universe is yung energy density contribution ng mga yon bumababa, lumiliit. So for baryons, lumiliit yung energy density nila by a factor of 1/8⁴. Proportional yung size ng universe sa A cube. So point is liliit yung energy ng baryons kapag nag-expand. Liliit din yung energy ng radiation kapag nag-expand. Well, nabaliktad ko pala yung baryons and radiation, sorry. Yung 1/8⁴ is radiations and baryons. But the thing about dark energy is yung energy density niya is constant. So kapag nag-expand ka or contract, it doesn't matter. The energy of the contribution of dark energy to the total energy budget of the universe is constant. So that means eventually habang nag-expand yung universe, as far as history is concerned, I mean cosmologists are basically historians of the universe. liliit yung energy ng baryons and radiation, you'll be left with dark energy. And what that will do is ipupush na lang yung components outwards. So by that, not sure how the big crunch would happen. The big crunch would happen if tanggalin natin yung dark energy component. Kasi now you're going to have typical gravity. Basically, gravity is attractive. So ina-attract niya lahat. So eventually, without dark energy, mag-compress yung universe eventually. But with the prediction for that, so to answer the question, so removing dark energy, assuming it's not there, but it's there, but assuming it's not there right now, then magko-compress yung universe. Well, as far as expansion is concerned, in the same way that it contracted to its state before contracting. So ayun yung ganun siya magko-contract, but that assumes that we're not detecting any dark energy. Though the dark energy is one of the biggest plot twists in theoretical physics, kasi hindi natin siya in-expect na nandun, and then through various observations, you calculate the energy budget, you're going to get 70%. So it means the biggest contribution to the universe right now, and we don't know what that is. Actually, ayan din yung malaking part ng work ko, and I'm sure dyan mag-revolve yung work ko in the coming years, talking about dark energy, trying to figure out what that is. It should contract in the same way as it expanded. If you're asking kung ano mangyayari sa Earth or the Sun kapag nagko-contract na siya, wala, kung Earth terrestrial yung observations, I'm not sure. But as far as the cosmology is concerned, yung distance between the objects sa universe, mag-shrink yan. Kasi by contraction and expansion, ang ibig sabihin yan, you pick any two objects in the universe, yung distance nila mag-shrink or magko-contract. So ayan yung ibig sabihin ng contraction and expansion ng universe. Hopefully that answers the question. Thanks for that.
Thank you also, Dr. Bernardo. We still have so many questions in the chat box, but I'm afraid that we cannot anymore cater those. Surely black holes are really very interesting to talk about. Again, we apologize if we can't accommodate all your questions, but you can send them and your messages in the feedback form, which will be sent to your emails after this session. Also, if you like, you can still stay after this session. We still have some networking, and you can ask those questions there. And again, thank you so much. Thank you so much. But before I turn you over to our host, can we give Dr. Reginald Bernardo a virtual round of applause, please? So that's it. I now turn you over to our host, Miss Ida. Thank you.
Thank you, Dr. Reggie, for such a wonderful talk, and also Professor Kenneth for moderating the session. Can we give them again a virtual round of applause, please? Okay, so now I'd like to call Dr. Merch Beldengal, faculty member from the Physics Department of Mindanao State University, Marawi, to give the response.
Hello, everyone. Can you hear me?
Yes, ma'am.
Yes? Okay. Hi, Doc Reggie. So I'll just read a few things that I wrote para hindi ako ma-carried away. So,
yes,
like the heroes in the anime series that we love to watch, I believe the participants here would agree with me that you and your team at NIP with Dr. Ian Vega are heroes of gravitational physics in the Philippines. And we really appreciate the way you trace the history of gravitational physics research in the Philippines from way back in 1971. So that's something that I did not know before. So from 1971 up to the present, yes. And this kind of information is very inspiring to physics students and also to early career researchers like me. And also, I have read the Facebook post of Dr. Ian Vega that was shared by the Samaang Pisika ng Pilipinas, and where he narrated the many challenges that your group has encountered when you started the group, and learning now that your group has succeeded in being a very important part in the bigger picture when it comes to gravitational physics research is indeed very, very remarkable. No? Ang haba ng pinagdaanan ng group. No? So it is sa post ni Dr. Ian Vega. So very, very inspiring
Yes,
as well.
actually.
And personally, I love how you encourage our student participants to pursue MS and PhD in the Philippines as an option, no? That
Yes, yes.
compared to, yes, it is also a viable option, hindi lang yung sa abroad, as evidenced by you, our first homegrown gravitational physicist. And maybe in the future, some of our participants here who are still high school students, maybe in the future, they would be one of your thesis or dissertation advisee at NIP or wherever you are, wherever you end up to be in the future. As you said, you're a free agent.
Yeah,
So,
sana.
yung iba dito might be your future mga advisees, no? So, and finally, I appreciate how you presented a reality check on the key issues when pursuing graduate studies in the Philippines para ma-set yung mga expectations din ng students natin. And these are very important points para sa mga future graduate students natin sa physics, no, when they make their decision to pursue MS and PhD. So thank you very much. And overall, this physics meetup has been a great experience. As always, no, Adele and the physics meetup team. So thank you very much. And thank you very much, Doc Reggie. See you sa SPP siguro. Thank you very much to you and your team for putting the Philippines in the map. Ika nga, when it comes to black hole research. So very, very timely. So once again, thank you to everyone and to the participants. So back to you, ating MC, Miss Ida.
Thank you, Ma'am Merchbel. Dr. Bernardo, would you like to say some final words before we close our session?
Yeah, so I think for the students, basically, well, ito yung palagi yung sinasabi, don't be afraid to try out new things. I mean, as far as gravitation and cosmology is concerned, kung interested kayo dyan, ang dami-dami natin di alam. People are going to tell you a lot of things. Try this and try that, but basically, and I'm sure about this, we're all struggling to see in the dark right here. We don't know what dark energy is. We have no idea bakit, palaging nag-a-appear ang objects sa universe in terms of pairs. So black hole binaries, stellar binaries, I mean, lahat sila naka-pairs palagi. So pinakamadami ang singles, I don't know, sa Earth. So sa rest ng universe, you always have pairs. We have no idea why. Madami pang existing questions, dark energy, dark matter. Check out yung story ni Professor Andrea Ghez, yung astronomer who won the Nobel Prize in 2020. Yung ginawa niya yung PhD niya, she basically just had a telescope. So yun yung advantage niya working at Caltech. May magandang telescope nila. Say you have 50 million or I don't know, 300 million. You buy a big telescope, 50-meter telescope, ayun yung meron siya. But she did not have any of the methods she needed that time. So she had to invent all of the methods that she needed in order to be able to determine yung black hole at the center of Milky Way. So sobrang inspiring ng kwento ni Professor Jez. I-check nyo din. And she's of course women in STEM, so check out that very inspiring story. Daming struggles. Well, she's one of a kind as well. So don't be afraid to try out new things. And yeah, I think that's it. Wala na akong maisip ngayon. So good luck. Huwag kayong matakot sa math. Hindi ako magaling sa math. Palaging may mas magaling sa akin sa math, then magtatanong ako sa kanila. So ganun nangyayari talaga sa research ko. And kung ma-stuck ka, that's very, very likely. Mas stuck ka for 1 week, 1 month, mas stuck ka for 1 year sa isang research problem, that's totally fine. And that's totally fine. Don't be discouraged by that. And very likely you talk to any research student out there, ganyan din ang state nila. So it's, yeah, I'm sure you can do that eventually. And do it closely with your friends. You have to stay sane. Kailangan may keep yung sanity while doing this kasi masyadong may yung research problems. You have to, and be human while doing all this. don't be attached to the world while doing all this. Yeah, that's my last words, I guess. Thanks.
Thank you again, Sir Bernardo. We will now have Professor Bien Butanas, the chair of the Physics Department of Central Mindanao University, for the closing remarks.
Hi everyone. Magandang hapon sa lahat. I'd like to thank the 400 participants who joined us today. And as I look at the Facebook page, we also have 2,000 participants. And I'm so happy seeing my good friend Dr. Bernardo, Reggie Bernardo, and then
Yeah, thanks, Bien.
so if I may share, matagal na naming nililigawan si Reggie to be our speaker. Kaso nga lang may problem about the internet, and as we noticed,
nakita niyo naman
may konting problema, but then thankfully he joined us today. Maybe he was touched by the recent development in the world of physics when the Nobel Prize winners were actually announced. So thank you so much that today you've inspired a lot of students in the country, and I would like also to thank these students who joined us. And if you notice in our promotion, we are actually partnered with several organizations in our societies in Mindanao. So I'd like to name them. So we have the Physics Student Society of the Western Mindanao State University, the CMU Science Education Society, as well as the CMU Physics Society. And then we also have the Caraga State University Physics Department, the University of University of Science and Technology of Southern Philippines Physics Department, and then the Bukidnon Physics Society, the Einstein Society of the Philippine Normal University at Mindanao, and we also have the Science Educators Guild at the Caraga State University main campus. Also, this is not possible without our partnership with Dr. Reina Reyes and the PINOY scientists organization, and then the Earth Shakers organization through Mr. I forgot the name. Sorry, Adele.
Ralph Abainza.
Ralph Abainza. So mahirap kasi i-pronounce yung last name. But then, hopefully, yung mga students natin ngayon na nakinig sa kay Dr. Reggie are inspired to pursue black hole physics and cosmology, kasi sa nakikita ninyo medyo kaunti lang yung nagwo-work dito, and then but ngayon unti-unti na silang dumadami, and hopefully magkaroon din ng someone somebody na ganun ang field dito sa Mindanao. So hopefully at sa ibang location ng Pilipinas din. Sana yun nga, yung mga professionals natin sa field na to ay dadami. So for that, thank you so much, and gusto kong pasalamatan talaga si Doc Reggie, and good luck sa postdoc niya later on sa Korea. Yun, thank you.
Thanks, salamat.
Thank you. Thank you, Professor Bien. Now, we would like to invite everyone to open their cameras if you are comfortable for a group picture. Because we will have 3 poses. So are you all ready? Please open your cameras for a group picture. Okay, so again, we will have 3 poses. Let's start in 3, 2, 1. Another pose in 3, 2, 1. And last one in 3, 2, 1. Okay, thank you so much. Once again, thank you for joining us in our physics meetup session today. For the e-certificates, we will be giving them next week, and to receive them, kindly accomplish the form which will be sent to your emails. In this form, you can also write your messages for our speaker. If you are still free, please join us in our short networking to meet our speaker and the organizers. Thank you and see you on the next session of Physics Meetup. Stay safe.